Free will. Seeing is believing. We all feel like we have free will, like we choose our actions, but science keeps telling us it's an illusion, and we've had no way to prove otherwise. What if there's a way to find and measure free will? What if we've just been looking in the wrong place? Can a simple example, like a kingdom and its king, help reveal where the causal chain begins to fail? This video introduces a new model that shows where to look and how to measure real autonomy, based on real-world information theory as presented in the book Darwin's Machines 2024. One king, no defenses. To understand how free will might work in any system, biological or artificial, we need a clear way to visualize how information flows. So imagine a kingdom that represents a complex system, like a neural network, a microchip, or the human body. Inside that kingdom, the king acts as a key decision maker, like a neuron, a transistor, or a node in a network. We begin our analogy with a king standing alone in an open field. No walls, no guards, no protection. When an external influence arrives, in this case a single enemy soldier, that soldier has direct access. The king's behavior is strongly influenced, even determined, by this one outside agent. In this scenario, free will is virtually non-existent. The environment has complete access to the system's internal function. The first buffer. Now let's add the first layer of defense. The king is no longer standing alone. There's a wall between him and the outside world. The soldier is still present, still threatening, but now they can't reach the king directly. The wall doesn't erase the threat, but it changes the situation. The king now has more options. This is the first sign of buffering, where external influence is reduced, delayed, or distorted. And it's the first step toward autonomy, not by removing the environment, but by limiting how much it can affect the system's key decision points. Internal causal networks. As the kingdom grows, it adds more defenders, messengers, and internal structure. The soldier is still outside, but now the king interacts almost entirely with agents inside the system. All external signals are routed, filtered, delayed, and in some cases dismissed before reaching the king. Inside the walls, a new pattern emerges, an internal causal network. Guards, advisors, and scouts influence each other, make decisions, and shape the king's behavior. The system is still governed by cause and effect, but now most of that causality is internal. The internal causal chain is beginning to separate itself from the wider external causal chain. This is where autonomy starts to grow, as the boundary between system and environment becomes more defined. Same signal, less access. The external signal hasn't changed. It's still the same lone soldier outside the system. But now we reassess what that signal actually does. The king, our key decision maker, is surrounded by walls, guards, and internal agents. The signal may still enter the system, but it's filtered, delayed, or even ignored before it reaches the king. This is a measurable shift in how the key decision points respond to the environment. And that shift defines autonomy. It's the relationship between the strength of an external signal and the system's ability to regulate or block its influence. As systems become more complex, they can increasingly buffer external signals, protecting or isolating their most critical components. Autonomy exists on a continuum, not all or nothing, but more or less. In highly structured systems, some external signals may have no measurable effect on internal behavior at all. Measuring autonomy. So how do we measure the autonomy of a system? The answer is simple. We measure how much influence the environment has on that system. As the internal system evolves, we observe how its key decision points respond to specific external signals. The more impact those signals have, the less autonomy the system has. The less impact they have, the greater its autonomy. If external signals consistently fail to influence the system's key decision points, that's evidence of emerging autonomy. Just like in our kingdom, where one soldier once had direct control over the king, we can now test whether that signal still gets through as the system becomes more complex. We can design a kingdom that allows many signals to influence the core, an open kingdom, or one that protects its decision points with layers of pre-processing, a closed kingdom. In engineered systems, we can tune this autonomy to match the task and the environment. That's what makes this model powerful. It turns free will from a philosophical idea into a testable and designable system property. Real, measurable, designable. Autonomy isn't a mystery, it's a measurable property of systems. As systems grow more specialized, they can filter, delay, or block external signals, protecting their most critical decision points. This shift is what allows free will to emerge as a real, testable phenomenon. Whether we're studying neurons in the brain, circuits in a chip, or nodes in a network, the principle is the same. We can track how much influence the environment still has, and how much control has shifted inside the system. Even a single neuron becomes more autonomous when its surrounding conditions limit what makes it fire. Just like a cell with a membrane or a kingdom with gates, autonomy grows as boundaries become stronger. And that's the power of this model. It applies across biology, technology, and everything in between. To explore these ideas in more depth, check out Darwin's Machines 2024, available now.